Hello, everyone. This semester, the first seminar today, speaker is the Dipendu Bhandari, your PhD scholar, right? So title is Investigating Leptogenesis in the Era of First Order Electroweak Phase Transition. Please start.
Thank you. Thank you for organizing my talk here. So, in this talk, I will just wrap up my idea like that leptogenesis, but in an era of first order electric phase transitions, to modify the scenario a little bit so that we can lower the right-handed neutrino mass, or mainly getting the more or higher rate of chance or probability to detect it. So I will start from the basic, like that we all live in the matter-dominated universe, and this asymmetry in the matter can be quantified as the ratio of baryon density to the entropy density, and it is measured from WMF or Planck data, and the measurement is of the order of 10 to the minus 10 order. So we have to explain this amount of asymmetry with a theory, but in normal, in the standard model, there is no such explanation to address or to tell the origin of this asymmetry, so that we need to go the BSM. So to dynamically generate such asymmetry, mainly the Sakharov's gave three conditions have to be and that have to be satisfied. One is the B violation, that is the baryon number violation. Another is the D and CP violation, and the third one is the non-equilibrium or out of equilibrium situations. So the B violation or baryon number violation, it is present in the standard model through Phaleron, where the transitions from the gauge vacua, they can generate a non-zero change of Chern-Simons number, and from that they can transfer to the baryon and lepton current. So B and L violating and B plus L violating. This Phaleron process can accommodate this type of violation, and also Phaleron process accommodate that B minus L is conserving. So B violation is present in standard model. Okay, and now comes to the C and CB violation. CB violation also presents in the standard model through the quark sector in the CK matrix element, but that the amount of the CB violation in the quark sector is not sufficient to explain that amount of baryon asymmetry. So also for this case, we need the BSM sector to accommodate the extra amount of C violation, and also the out of equilibrium situation, so that the asymmetry can survive, is not washed out. So in the literature, the most promising mechanism to generate such asymmetry is the leptogenesis, and also at a first and simplistic case with a hierarchical right-handed neutrinos. So in leptogenesis mechanism, what people do that they extend the standard model with 2 or 3 generation of right-handed neutrinos, and they couple this right-handed neutrino to the lepton doubling and Higgs through this Yukawa, and this right-handed neutrino have a Majorana mass term. So this is called the type 1 seesaw Lagrangian. This actually explains the smallness of active neutrino mass in our standard model. So people just try to see how this model also can also be generate the lepton asymmetry or the baryon asymmetry that was measured. So the idea is that this right-handed neutrino can decay to LL and H through this coupling. So, and during the decay process, these three conditions have to be satisfied. So the out of equilibrium situation, CP violating, and the lepton number violating. So out of equilibrium situation, that means if the right-handed neutrino decay at some temperature, then that temperature is less than its mass, then it can decay to LL and H, but there's no reversible process or inverse process. LL and H can produce to N. So this type of situation, in this type of situation, N can decay in a one way to lepton and Higgs and produce a non-zero lepton number. And from this lepton number, or you can assume generate the B minus L asymmetry. Now this B minus L asymmetry produced at some scale that is converted to the baryon or B asymmetry to the spheroid, as the spheroid is a B violating interaction and also B minus L conserving interaction. And so there's a relation from B minus L to B, how much amount of B minus L asymmetry can be transferred to B asymmetry to the spheroid relation. So through this process, we can get a baryon asymmetry. Now, what is the amount? So it is seen that to satisfy the observed amount, that is of the order of 10 to the minus 10, the right-handed neutrino mass is very greater than greater than or equal to 10 to the power 9 GeV, and that is a huge number. So, and also it's, from detection perspective, it is a little bit difficult to produce this kind of heavy particle in our recent, in our experiment to detect it. So people are trying to, to throw different model or different theory to lower down this right-hand neutrino mass, so that with low mass right-hand neutrino also we can satisfy this neutrino mass as well as this baryon asymmetry. So in this direction, also people find some way, that is the leptogenesis with the resonant type scenario. So in previous case, we at first considered that these right-handed neutrons are hierarchical. That means we extend the standard model with 2 or 3 generations of right-hand neutrinos, and that 2 or 3 right-hand neutrinos, in between them, the mass scale is a hierarchical. There is a much difference between their masses. But if we consider that we have suppose we have 2 right-handed neutrinos and they are quasi-degenerate, for that case, with low mass also, we can generate or we can enhance the CP asymmetry of the order of 1. Mainly here, the CP asymmetric generation, the parameter that depend, in this case, the CP asymmetry mainly depends on the mass difference between those 2 right-handed neutrinos, not the actual, the individual masses. That's why if we can tune the mass difference accordingly, we can get a large CP asymmetry even when their masses can be low, individual masses can be low. So, okay, this is a good scenario. We can lower down the right-hand neutrino mass. As so, for this scenario, for this case, we get the baryon asymmetry as well as the neutrino mass problem solved. But suppose if we go down this right-handed neutrino mass below this scale, that is mainly the Electroweak symmetry breaking scale, so roughly 160 GeV. So if we go down below this scale, mass scale, with that right-handed neutrino, then we faces 2 problems. So below T Electroweak, N to LL bar H decay is kinematically forbidden due to Higgs now gets a wave, and Higgs is massive, which is the 125 GeV mass. So suppose if we have a right-handed neutrino of the order of 100 GeV, this 100 GeV right-hand neutrino cannot decay to lepton and Higgs, where Higgs is a 125 GeV mass.
But the thing is that H can be an optional, right? N can decay to lepton plus optional Higgs to DV bar. What about that? I agree that the two body it will be kinematically off. But what about 3 body? Lepton plus DV bar. Still I can generate this.
And the same amount?
How will be suppressed?
Probably suppressed. Because these are offset, so this is the mediator 1 over the MH square. Maybe not that much amount.
But maybe some amount can be generated.
Yeah, maybe so.
Sure. So I'm not familiar with this subject, but my question is more conceptual. So this resonant leptogenesis, it's more in some sense available for experiment, right? Because the assumed mass of right and interiors are lower.
Yeah.
Is there any other way and reason that this model is preferred, except the fact that this has it? So the original leptogenesis model, we have recommended generate two methods that so we cannot test it.
Yeah.
But this one may be available for experiment. That's good. But beyond that, not just about availability. Is there any better reason that this is better? Derived sense?
I don't think so. I mean, people just, I think,
Also, there is probably a related question. If you have degeneracy, you can have a lighter mass. But this is also true the opposite. Suppose that nature has decided that the neutrinos are degenerate. Then, in order to have the correct amount of lepton asymmetry, so baryon asymmetry, is it automatically true that also the mass of the neutrinos are low? Is a prediction, or you can have still heavy? You understand? So, because nature could decide that the neutrinos are degenerate. It is it's not our choice. Suppose that the neutrinos are degenerate. Is it automatically true that then, in order to have the correct amount of baryon asymmetry, the neutrino mass has to be low? In other words, in this case, it's kind of a prediction. In the other case, it's a possibility. So do you know? Maybe, probably, depending on the Yukawas, it's not true. You can have both cases.
yeah, I mean, so, yeah, I mean, so for that, I mean, for that part of questions, I don't think there is other, I mean, aspects of introducing this resonant leptogenesis case, except the theory, I mean, the experimental perspective, or because, I mean, yeah, or in that perspective, yeah, I mean, if
It's a
nature,
possibility.
yeah, it's a possibility, nature just chooses that this is the case.
Another thing that can also be added is that for this low mass right-handed neutrino, since you are also satisfying the neutrino mass, the low mass will ensure the Yukawa coupling to be small. That will also ensure the right-handed neutrino that will decay will be out of equilibrium. Because the coupling goes down.
Yeah, coupling goes down.
So out of equilibrium decay it will ensure.
Yeah, I mean,
to generate the lepton asymmetry, which will be converted to baryon asymmetry.
yeah, I mean, this lower, I mean, from this lower Yukawa coupling, the out of equilibrium situation also, I mean,
automatically the Sahara conditions.
yeah, in also, I mean, this kind of idea is mainly used in also the ARS mechanism, where this two flavor of right neutron is oscillating with in out of equilibrium and transfer the asymmetry to lepton favor, but that oscillation also out of equilibrium, but in that case the mass can be also lower than 30 GeV also. So their case, what happens, the Yukawa coupling is very low and very, I mean, feeble. That's why they can out of equilibrium way, I mean, in an out of equilibrium way, they can oscillate and transfer the asymmetry. Yeah,
of course. So one should consider that it should be better. So, from the point of view of the beauty of the model, a heavy neutrino implies that also the Yukawa coupling is a working one.
Yes.
And this is better because you ask why the Yukawa coupling of the neutrino is 10 to minus 6 and the Yukawa coupling of the electron is 1. In other words, there are pros and cons. The other model, when you have a neutrino with 10 to 9, you cannot measure it as an accelerator, but the model is probably more beautiful in the sense that all the couplings are the same.
yeah, listen this.
Here instead you have to tune the coupling of the Yukawa coupling to 10 to minus 6, but in this you have the bonus that you can measure.
Yeah, you can measure the state.
This is the non-hyper.
So one problem is that it cannot decay out of I mean, to kinetically to lepton and Higgs to generate that kind of asymmetry, I mean, that much amount of asymmetry. And also the below T electroweak, if somehow the lepton asymmetry can be generated, so below T electroweak due to the Higgs wave, the Faleron rate becomes exponentially suppressed and out of equilibrium. So the generated B minus L asymmetry cannot be converted to the baryon asymmetry below this scale. So with this kind of low right hand neutrino mass below 100 GeV, we cannot get any Leptogenesis scenario.
The suppression is at 160.
Yeah, I mean the failure rate suppression starts from below 160, because below 160 he starts to get there, and at 130 pheron is completely out of equilibrium.
So between 160 and 130.
But there's exponential suppression. So if you generate a lepton asymmetry, you cannot, I mean, then you have to check how much asymmetry survives or can be
You need
converted.
to be above 160.
Yeah, in a minimum way. We have to be 100, above 160 for this case. So another interesting thing is that suppose for instantaneous reheating case, I mean, where the universe can have the highest temperature of that reheating temperature. So if that case is considered and the heating temperature is below, again, below this T electroweak, as we know we have a bound up to the BVN temperature, the heating temperature can be that much amount of low. So if for that instantaneous reheating scenario, reheating temperature is below T electroweak, then the universe never reaches above T electroweak, and for all the time of the universe history.
So in other words, we have no idea what was the maximum temperature of the plasma in the early universe. The only thing that we know is that it should be above, I say, a few MeV from maybe.
Yeah.
So it's a free parameter. So you are saying, in case it is very light, then of course you cannot have leptogenesis.
Leptogenesis, because all the time this phenon is out of equilibrium.
So unless it is higher than 160. So
Yeah,
this is the
if you, and for that case, if M1 is if greater than 160 also, for that case you cannot generate the baryon asymmetry through leptogenesis mechanism. Also there are some direct baryon asymmetry production mechanism. There may be, I mean, the baryogenesis mechanism, direct electric baryogenesis like things. But if you consider the production or generation of baryon asymmetry through leptogenesis mechanism, then below this, I mean, with this condition, no other existing leptogenesis scenario can work. So we just try to evade these two problems here with incorporation of first order electric phase transitions, that even with T heating that much amount of low, less than T electroweak, from leptogenesis we can generate the baryon asymmetry, and also with a mass M1 which is below 100 GeV, we can still get a baryon asymmetry.
Okay, so the question is that in the standard model, the electroweak phase transition is not first order.
First order, it is only a mere crossover.
So in the standard model, if you just add the Yukawa coupling, this is the situation. Now we need to modify the model.
Yeah, I mean, we just, I mean, have to achieve or realize a first order type things by some addition along with the standard model. So here, to be in minimal scenario, okay, before going to the first order phase transition scenario, I just briefly discussed about the phase transitions like things. So phase transition generally of two types, one a first order and then a second order. So in second order transitions, what happens? Suppose at high temperature, the scalar field sits at this zero minima. Now, with gradually decreasing the temperature, this potential develops another minima, which is become global, and then the scalar field from the previous false minima is gradually shifts to the newly developed global minima, and this TC is called the critical temperature. So this is the second order type phase transitions, and here the transition of the scalar field from the previous minima to the later developed minima is a continuous. It continuously rolls down, and so this is called the second order type transitions. But first order, what happens? So as like second order at high temperature, it has a global minima at suppose phi is equal to 0. Now at some critical temperature, a second minima, which is phi, where phi is non-zero, develops in between a barrier between them. And below TC, that newly developed minima will be now global minima. Now this at some temperature below TC, the scalar field which sits at that place goes from this to this but due to a barrier, it cannot be directly over, go over the barrier because it sits there and it has not enough kinetic energy there. So it basically tunnels through this barrier from this false minima to the true minima. So this kind of phase transitions is like a discontinuous type phase transitions, and it's called known as the faster phase transitions. So mainly what happens that it proceeds to the bubble nucleation. Mainly the bubble of in between the bubble, the phi is non-zero, this is broken phase, and now it starts to expanding the universe, and the outside is phi is equal to 0 phase and covering the universe with decreasing in temperature, and after at a certain temperature, all the universe will fill up with bubbles. Phase transition completes, and now the scalar field we have a non-zero phase. So in this way, this first order phase transition goes on. So to be minimal, we just add dimension 6 operator of Higgs.
So in the standard model, you have no pair.
No, so
So you need to add something else.
this
Okay, you add an
Box.
effective operator.
only. In standard model, we have this only 5 square and 5 term. With this, we cannot get any faster type things because we cannot generate the barrier between 0 and non-zero minima.
In other words, you have a free parameter lambda.
Lambda here. So that lambda mainly helps. So, okay, so we then on top of that, we take the Coleman-Weinberg corrections, one loop, and the finite temperature corrections. This is the cool potential. This is the counter term. Counter term adds because this due to this adding of this potential, the Higgs wave at 0 temperature can be shifted. So this counter term helps to fix it at 6 dB wave. And here we also incorporate the DG corrections. DG correction is implemented through the Parwani summations. So Parwani summation tells that if we replace this field dependent mass with the field dependent, the field dependent mass square with the field dependent mass square plus the size of that particle, then the DG correction will be taken. So after incorporating this Coleman-Weinberg, finite temperature, DG corrections, counter term, you have to study the potential to get a faster type things. So now here.
So some question. So in the so you said in the sphellaron case, sphellaron is this bubble. Is that what you call sphellaron?
Sorry, can you speak here?
The sphellaron is the bubble solution or?
No, sphellaron is not bubble solution. Sphellaron is the solution mainly sphellaron is the transition of two SU2 gauge vacua between two SU2 gauge vacua.
Okay. So you have not mentioned yet. Okay.
Yeah.
And the question was, how it saves B minus L rather. So how can so in other words, B and the L, the sum is not preserved, but the difference is preserved. So question is whether that especially depends on the gauge groups or that kind of thing, or just from the gauge theory itself, I do not see why it should be like that.
No, it's a non-perturbative effect of the standard model, but is only possible at high temperature. At 0 temperature is exponential.
It's not possible, yeah.
So in the standard model, the baryon conservation is accidental. The proton cannot decay to anything. There is no particle to which it can.
And the baryon number and the lepton number is accidental symmetry.
Yeah, they are accidental. There is no explanation why baryon and lepton.
So in the case of the instanton, roughly speaking, sphellaron is the half of the instanton, they say. And in the case of instanton, the way that they are breaking the baryon number is there seems to be some zero mode playing important role. So it's a similar argument goes here, and there is a zero mode for fermions, both for quarks and leptons.
So probably
and
you should show a plot like this one.
Yeah.
Sphellaron.
Yeah.
So anyway, so since you
Yeah,
have
man.
not mentioned, yeah, okay, so it's not
So,
the
Yeah, so
Can-
you can think about an interaction where leptons can be converted into baryons, but only at high temperature.
Yeah.
It is allowed by the standard model,
standard model.
but it's non-perturbative. So
Yeah, non-perturbative.
it's non-perturbative. So it's not something that you can find in an accelerator.
I see. Okay, so that's I mean the inside the structure of the standard model.
Yeah.
Okay, good. Okay, okay. Thank you.
Yeah. Okay. Okay. So we have to study this full potential as well to take care of, I mean, how the first order extension goes on like this. But before that, to simplify the calculation or for a simplified demonstration way, we just here approximate that full potential for with a high temperature approximation, where these thermal functions can be expanded with m square by t square as we consider high temperature. So m by t is less than 1, less than 1. So we can expand it, and if we expand it, we just restricting the terms up to order t square in the potential. So
here we are assuming that all the masses, the m, what is m? The
m
mass?
is the, I mean, the field dependent mass of the each particle or each field that's
So you
present,
are summing over
all the particles and
in the
fields.
loops.
In the loops,
you have
yeah.
all the standard particles, and so in other words, which particles are you including? The temperature you have in mind, it has to be much larger.
Much larger this field. I mean, suppose I mean, with high temperature, I mean, suppose at high scale, above 100 GB or 200 GB, like things. So where up to that Higgs doesn't get a mass, these all have the massless type things except the thermal mass. So according to that, so for that case, by considering the high temperature approximation, m by t is less than 1. So with that assumption, we just expand it. But this for the just time, for the time being. This only for the time being. That if we consider the high temperature and restricting the term up to order t square, then we get in phi square as CHT square term, and in phi core a correction. And if we go beyond the t square, we get a term of the order t. So t, and then we get a constant or log term with higher dependence of phi. So we just neglect that term. Only just restricted here up to t square to easy the calculation for the time being. So this is our potential now. So here now we are trying to, limit our lambda value, the cutoff scale, for which we get the first order phase transitions. So if we plot this potential,
Can you please move back? Very nice question I have right now. Let's forget about the 5 field extension.
okay.
Okay. Now let's say you introduce thermal correction where your standard model Higgs have a thermal mass, right? So it's going to right-handed different electron will open up the decay channel, which will also be CP validated. So the thing is that why doesn't it generate sufficient electron asymmetry to get the baryogenesis? Because at that time your speleron will be also be present.
Yeah,
H2 into NL, because it will be very heavy. If I take the Higgs thermal mass.
Okay. So if you take the Higgs thermal mass very heavy and then right-handed neutrino mass less than that mass so that it can decay. So mainly the Higgs thermal mass is of the order of 0.6 into T.
Yeah.
So
let's say I'm sitting at 1 TeV.
Yeah.
So my Higgs can decay to right-handed neutrino and lepton, right? Which can generate the asymmetry as well.
Yeah.
Lepton asymmetry as well, which can be also be converted to lepton baryon asymmetry because speleron is sufficient enough.
But Higgs is in equilibrium at that time. So the inverse process can also be there.
What about right-handed neutrino Yukawa? Because the Yukawa coupling is Higgs can decay.
Yeah, right? Then the inverse decay is also there, no? H2NL and NL2H, if you have something like high temperature, you consider.
So you mean all the masses are thermal, so the
So the
Yeah.
water will be there.
Mass is thermal, so is all is
it's
in
not out of
a thermal bath. It's not out of equilibrium. Okay. So if we plot the potential with different lambda value, we see the change in the barrier height. That with increasing lambda, the barrier height is decreasing.
So lambda was in the
At the
denominator.
cutoff scale, the 5/6 by lambda square, that lambda,
So what was in the denominator?
denominator and the operator. So with increasing lambda, the barrier height is decreasing. So at some lambda, the barrier height is so small, or so, I mean, it seems like flat, though it has some small bump, but it is very flat or very low height. So below that, if we go below that 750, the barrier height is so small that there is no point of talking about the faster type phase transitions. I mean, the barrier is actually disappearing.
So in this plot, there is only a free parameter, lambda.
Only frequent lambda.
So can you remind me, how do you fix anything else? So
How do
you fix the Higgs boson mass?
Yeah, Higgs boson mass and wave. I mean,
So then you calculate TC.
yeah, with this you can fix the other parameter with mass and the wave.
So it's just you calculate TC, and then at TC you calculate the barrier.
Barrier.
And it depends on
Lambda.
But why lambda has a minimum as a maximum? So what happens with even larger one?
Yeah, I will
Okay.
come to that. So with low, I mean, with
First
increasing
off,
lambda, yeah, with increasing lambda, the barrier height is decreasing. So up to the, I mean, up to upper limit of lambda, we have to stop so that we can get a sufficient faster type transition. So we just limit, let's say lambda is 750 GeV, and below that we do not get. Now,
so the other way around, what happens with lower values if you keep going down? So that the red plot
will go upward also.
so it
Yeah.
continues to go up.
Yeah, so we also limit the, I mean, lower value of lambda for
Because the
up to
value
which we can get,
Because the tunneling becomes
then very suppressed
so there is a kind of minimum
and maximum value. I mean, yeah. So this is the false vacuum decay case. I mean, suppose at first the field is displaced with a very high temperature. At TC, the critical temperature, a barrier is generated between this newly developed non-zero minima and the zero minima. Now, at some temperature Tn, suppose, which is less than Tc, if this condition satisfied, but this limit is the false vacuum decay rate, which is quantified as this. And if this false vacuum decay rate is greater than or equal to the Hubble expansion rate, now this particle can tunnel from this false minima to the true minima. So these conditions actually tells at which temperature this tunneling can happen, and that is that temperature is called the nucleation temperature, Tn.
Tn is below Tc.
Tc.
So Tc you had a number of order 80. In
Yeah,
the previous
if
plot,
we-
you
yeah,
had 70,
80.
60.
Hmm.
And so Tn, how much is it?
I mean,
So
suppose
it's predicted. Everything is predicted.
Yeah,
Once
I
you
mean,
fix lambda, everything
everything is
but
predicted.
no. And so what is the value of Tn?
Tn value I just show you in the next plot. So here just, so from this condition, we can infer a quantity like NV. NV is actually the number of bubble that is start forming when the tunneling starts. So the temperature at which the probability of forming at least one bubble per horizon is of the order of 1, we call that temperature is the nucleation temperature. So if we plot this NB with temperature, suppose with a lambda is 586 GeV. So this is a cyan color line. So we see that up to some temperature, I mean, suppose here from this plot 590 is Tc, so 586 a lower little bit of Tc is there. So suppose let's say 60 GeV Tc. So from TC, we just see that there is, I mean, the number of bubble is very low, below 10 to minus 4, and now around 36 around, suppose. Now the number of bubble is now increasing, and around 30 GeV, it reaches of the order of 1. So that temperature is actually mathematically determined to be the nucleation temperature, and below the temperature it increases a smaller one, I mean increases a little bit, and then just nucleate around the, throughout the space. So this is the case of 586 GeV, from and by which we calculate the nucleation temperature, that is the tin is 30 GeV. So here we get a 30 GeV temperature as for nucleation, but the critical temperature is of around 60 GeV. So I mean 50% is decrease. So now again for lambda is 585.7 GeV, closely spaced value. We see that again, we see a number of bubble is of the order of 10, 1 at 27 GeV temperature and then goes on. But if we choose lambda is 585 GeV, now the number of bubble is not reaching of the order of 1 till the 0 temperature. That means here the barrier height is so much, the probability of tunneling the particle from 0 to non-zero value is very less, and actually the bubble is not nucleated in that case. So we limit in this way what will be our minimum or lower limit of capital lambda to work with.
So you have a range between 585 and 650.
750.
That's 750.
750 GeV.
So this is the range.
This is the range where we can get first order phase transitions successfully.
So question. So
Yeah.
all your bubble formations and first order phase transition existence, that seems to depend on the cutoff scale lambda.
Yes.
Is it physical? So cutoff is a really physical quantity, or I do not understand why it should depend on lambda. So is lambda supposed to be going to infinity or something, or?
Yeah, if lambda goes to infinity, then then there is no adding the point of the dimension system, because only the standard model we get. So we have to lower down the lambda so that the new physics can affect.
No, this lambda is just a coefficient, a free parameter. So you
Yeah.
in the standard model you have quarters.
I see. This is okay. This is
They
not
need a
renormalization
sixth power.
lambda. I see.
Yeah, the non-normal.
Get it.
So you imagine that you have some new physics and this is an effective.
Okay. New physics occurring. The new physics coming
yeah,
scale.
there is some UV completion also. From that you can generate this dimension 6 term also.
In other words, you
Okay.
can ask if you have some kind of full models that.
Yeah. Also, in literature it has.
Another thing, so thing is that after 585, your barrier becomes too high that no transition may take place. But naively, if you look at this lambda from 585 to 586, the change is not that much. It's just 1 GeV.
Yeah.
So my question is that this lambda is so sensitive that by changing 1 GeV, the phenomenology actually changing.
It's just how should I answer this in physical way, because it's mathematics.
There are many uncertainties which are around 1 GeV.
Yeah.
10 GeV is something, but here just changing 1 GeV without something getting changed. So that is very curious.
Because if you think it's a very tuned so you need the barrier, because without the barrier you don't have first order physics. However, the barrier implies an exponential suppression, so you cannot play. So you need a barrier, but not too much, just a little bit. So it's a model where there is quite tuned.
Just you have to that the decay rate have to just overcome the Hubble expansion rate. If it's not, then it will.
So it's
not
kind of like fine tuning this cutoff, right?
Yeah, you might wonder whether there is a fine tuning. Yeah.
Fine tuning kind of like, yeah, I mean, you can say that below this lambda we cannot go.
No, because you can see that just by changing by
Yeah,
just
also.
one GeV, the things are changing drastically.
It also depends on, suppose, this type of calculations. This is the case.
Okay, let me see whether I understood correctly. So your new physics is right-handed neutrino, is that right?
Yes.
No, the
And
answer is yes.
And also the capital lambda.
Yeah, so he has a 5 to
Can
the
I
6
see the capital lambda where it
Yeah.
occurs?
So you see 5 to the 6 is not present in the standard.
Oh, I see. Okay, so just the presence. So actually, in the standard model, you can calculate the 5 to the 6 coefficient, right, through the loop effect and etc., right?
Yeah.
Is this lambda is really your parameter, or
It's a
usually
parameter.
I
It's a-
expected what is the contribution from the standard model to the lambda?
In this case, this is a pre-parameter, and we just limit this through the first order phase transition perspective.
So in the standard
Yeah,
model,
but
it's not there. The coupling is not there, and the phase transition is how is it called? A crossover is
only the simple crossover.
There is no bubbles.
No bubbles.
And in this game, you need the bubbles. You need the coexistence of the two phases at the same time, and the barrier.
Okay, I understand. But I mean, if you look at the phi square and the phi fourth term, there is usually from the standard model Higgs sector, the mass terms and the lambda h, and also temperature dependent pieces. And at least from the loop effect, I think any higher order of the 5 or like a 6 or even higher will be produced even though the coefficient is small in the standard model.
Yeah, if you don't,
I'll be happy if you just add first the standard, at least a one loop standard model value, then plus additional thing, that would be much better for me. But it seems that you are just putting everything at capital lambda, and then it seems to me that the capital lambda is not from the all new physics. It's just effective theory. But the standard model may already contribute up to some. I'd like to know up or what is it in terms of the mass, or whether it is much lower than 580 or there's a 750 GeV or higher than that. I'd like to see so if the like a standard model contribute bigger number than lambda equals 750, you showed that there is no first order. Then there is a point that you may just introduce some small to make it smaller, introducing some new physics, right?
Yeah, I mean,
but it seems that that's not the way you are doing.
Yeah, I just here add this term, and with this we just play with the how faster can be achieved. So in between standard model, there is also, if we, I mean, calculate the loop, and if we in one loop in only from the standard model, there is a term T phi q. This term will appear in the potential, and this term, from this term you can generate a barrier in principle with the standard model without introducing this term. So what happens that the coefficient of that term that is generated only from the loop effect of standard model, that is minus e suppose coefficient T phi q, that value of the is very less, so that the barrier height is, I mean, you cannot see the barrier actually when you plot the potential. So here actually this term helps to generate the barrier. So if we, when I add this type of corrections in standard model, we actually already took into the already present standard model one loop correction, and as well on top of that this correction adds. So we did not cut any term or any corrections from standard model. We take all the standard model correction from T level and one loop, plus we add this type of new physics only.
So what you're saying is that the standard model one loop will not contribute to the 5 to the 6th, and it will contribute only up to 5 to the 4th? I don't think so.
Sorry.
I think, I mean, the standard model one loop may contribute any 5 to the 6 or 5 to the 8, any powers, but and with the coefficient very small, I think, isn't it?
That I tell that if you go phi q term, that coefficient within standard model is very small. So if you go phi 6 and greater than that, the suppression is much more.
Right. So I see. So in that sense, maybe I can think that you are neglecting that small standard model coefficient
So we can assume that
contribution
this term
in 5 to the 6. Okay.
So we can assume that 5 to the 6 divided by lambda square overwhelms every contribution that counts.
Right. Overwhelms the standard model results. Okay. Okay. Good. I understood.
Correction that you were introducing.
Sorry, leading?
This is the kind of leading order correction that you are introducing.
Yeah, in
through new physics.
Yeah, through new physics, mainly.
Yeah. And other like next latest order.
Yeah, stronger
corrections.
Correction will be there. So here we get that we can, we can limit the capital lambda to a lower value so that the first order extension can be happen and complete. So suppose let's consider, we see from the figure also that lambda is of the order of 586 GeV around. And is the interesting point is that corresponding to that lambda, the nucleation temperature is of the order of 30 GeV. This is very less. So this is the main point here. So here, we just plot from the previous plot the number of bubble for lambda 586 and 585, and below corresponding these two capital lambda value, we plot a quantity called P of function of t. P function of t quantity is the probability of a spatial point to remain in the false vacuum state. So that means if Pt is 1, so that point in false vacuum state, and if Pt is 0, then that point is converted to the true vacuum and it is now inside the bubble. So for lambda 586 GeV, the sign.
What do you mean by spatial point? So
It's a universal's point. Universal's one point. The space. The space of the universe and one point or one region. Suppose things. This type of things. What is the probability that for that region to go from false vacuum to a true vacuum phase as the bubble expands? Suppose the bubble expand from that corner, it takes some time to that corner or this corner, in different time. So there's a probability of that point, that point probability of to remain in false vacuum state, and that point's probability to remain in false vacuum state is different with temperature.
If you wait enough, then eventually all the space will convert.
So all the space actually convert
at a particular temperature,
particular moment. There is a function of t, that's why.
Okay.
It's a function of t. So with every t, the probability is that.
Suppose that this probability is less than 1. Suppose that it's 0.5.
Okay.
Does it mean that half of the universe is in one phase and half of the universe is in another?
Yeah.
You should read it in this way.
Yeah, that is this way.
And that's the reason your green line doesn't
So green line is the 585 GeV where we see that the phase transition doesn't complete.
Yeah.
So we see that up to geo temperature it's still very high. Up to the 0.8. So the space is not converted to the true vacuum. So for this case, the phase transition cannot be happen. But for this 586 GeV, where the NV is of the order of 1 at some temperature and then goes, we see that at 30 GeV till it is the universe is in false vacuum. Now below the temperature, it starts to decreasing. That means the universe starts to convert to the true vacuum due to the bubble nucleation case. And around this temperature, all the space are covered by the true vacuum bubbles.
The green part, it means that the barrier is so large that
it cannot tunnel.
Basically, that you don't form the bubbles in the first place.
Yeah,
so you form
bubble is not forming actually. Or yeah, I mean, bubble is forming, but it cannot go beyond a critical size. Though for that it can expand, because if it can something little bit of grow, but due to the Hubble expansion is very high, it again sink. So it have to grow up to a critical size. For that, it cannot shrink due to the Hubble expansion, so that it can then after that it can nucleate throughout the space. So up to this nucleation temperature, as the universe falls, I mean trapped in the false vacuum, so you use the fact that now up to that the Higgs wave is zero.
the Higgs value
Is zero, as it is still in the false vacuum state. I mean, till it's not tunneled to the true vacuum, where the Higgs wave is non-zero.
So you are tuning the system in such a way that the universe is in a metastable
Metastable
situation.
state, yeah.
So you are pushing this to the limit.
Limit. I mean, how far we can go? I mean, how far? How low? How to? I mean, up to
From the
low
energetic
temperature.
point of view, it should go in the other minimum, but
Yeah, but we are
it's a
trapped.
metastable. state.
Metastable state due to a barrier in potential,
So the barrier is delaying
delaying the
this
transition.
and you are playing this game because you want to lower it.
That lower the temperature. Yeah.
And so your statement is that with this particular model, so if we add just this effective term 5 to the 6, the minimum possible temperature is 30 G.
30 G. Around. So below 30 G, I mean up to 30 GeV, the sphelon is now in equilibrium. So if the sphelon is now in equilibrium, now we can think of the Leptogenesis scenario here.
So this is because the leptons and quarks they are all massless.
Massless.
And so that's why it's internal.
Yeah, Higgs also. I mean, Higgs also doesn't have wave.
And the Higgs doesn't have one. And so in this way, this is not what happens normally.
No, normally
The sphaneron is completely suppressed.
Suppressed, I mean,
because you already have the wave and you already have mass and so on. But in this particular case, the universe is delayed, the mass particles are massless, there is no wave, and so the sphaneron continues to be internal. And this is the
idea.
special
feature of this. Yeah, introducing the first of phase transitions here. I mean, normally in standard model, the sphaneron is already decoupled at 130 around. So below this, we can go.
So in other words, in the standard model, the temperature where the sphaneron is suppressed is related to the heat to the wave of the Higgs. But when the wave is zero, this can
go to. I mean,
as long as
the wave is zero, it can mean in thermal equilibrium, because the transition in gauge vacuum is already, I mean, is happening.
Yeah.
Okay. So here, due to the introduction of this.
Sorry. So this means that the sphaneron interaction is happening outside the bubbles, but inside is blocked. And the question is that these bubbles remain, the volume of this bubble remain very small up to very late.
Yeah.
And most of the universe is outside the bubble, where instead the sphaneron is active. Yeah. So if you have this decay out of equilibrium, it can be converted into that.
Yeah, outside the bubble.
Out of the bubble.
So due to this introduction of this first electric phase transitions to case we get that till Tn we have the Higgs wave zero, all SL fields massless. Now if we consider the right hand neutron mass, which is greater than the nucleation temperature and even below the is the mere example like things that the gauge boson mass also, it can directly decay out of equilibrium with lepton and Higgs, and this is the first time we show that. Even if the actual mass of this right hand neutron is less than the Higgs mass, and this produced lepton symmetry can be converted to the baryon symmetry as the spheron is already in equilibrium up to that temperature. So the low scale is also possible. Now the reheating case, if the reheating case is if the reheating temperature of the universe below 130, no other existing low scale leptogenesis can work, but in our case, it will work because sphenon is now not decoupled at 130. It is up to still equilibrium at 30 GeV. So these two obstacles that was there in the literature, we just invoke with the introduction of only the first order phase transitions. And for low scale the low scale leptogenesis, there are various mechanisms. One of the ARS mechanism. So for ARS mechanism, the right-hand neutrino mass can be even lower than that. I mean, around 1-2 GeV also. But yeah,
2 GeV?
I think
Yeah, 1-2 GeV.
1 GeV also.
Asymmetry is converted through oscillation.
Oscillations.
Oscillation.
So, but from
Not the alto.
no, yeah, I mean, not from decay. I mean, not from decay. This is a different mechanism, a different way. But with this low mass, directly decay to lepton and Higgs, there is no work.
I think that ARS mechanism that you are referring to, that oscillating, producing asymmetry. Right?
Yeah, in ARS,
Yeah.
ARS. Yeah. Akhmedov, Rubakov, and Saposnikov gives the mechanism. Okay, so we just now study the resonant leptogenesis with two right-hand neutrinos with this minimal scenario and solve this simple two-coupled Boltzmann equations and get the bioinosymmetry. So to get the bioinosymmetry, we scan our parameter space with delta m with this range and the imaginary part of theta r with this range. And
now I'm confusing. Now you're combining together resonant and also so
no,
this is another.
No, not this. Yeah, we just with this introduction of this first order phase transitions, we just study resonant leptogenesis
Within this
model. And for that we add two right-hand neutrinos and study the Boltzmann equation to get the bioinosymmetry and this. So I mean, we just study here the parameter space. So for this parameter space, we scan over delta m because for every delta m we get a different CP.
Can I say this that by introducing the cutoff scale, you will change the speleron decoupling temperature. Along with the right-handed neutrino, we are changing lepton asymmetry to baryon asymmetry because the speleron is available at low temperature. Means like two parts, right? First is like using the cutoff scale to lower the speleron, and right-handed neutrino to generate the asymmetry to convert to baryon asymmetry. So another question is that during the calculation of this Boltzmann equation, so are you considering flavored democratic leptons?
Yeah, no.
Yeah, it is like flavor leptogenesis.
Yeah, we don't do the flavor calculation. It is only
flavor identical in this case.
Yeah, I mean in the non-flavor case. I mean in flavor case, somewhat I think.
But how will you justify the flavor identical at such low temperature?
Yeah, this is not just flavor, but if we do the flavor also, there is a 10 to 12% change of these values. That's why we just, I mean, do in a simplistic way because that's in way. I mean, suppose
at low temperature,
flavor is important. Flavor cannot be. Yeah, flavor cannot be.
Cannot change because tau factor can easily.
Obviously. In low temperature leptogenesis, flavor is important.
Flavor is.
Yeah.
But is flavor identical?
Yeah, I mean, with flavor, here we take flavor identical, and if we go down, I mean, do the calculation with flavor also. This suppose with 10 to the minus 12 delta m, we get asymmetry. Then suppose with flavor, we tune something else with that, so that we get the same amount of asymmetry. Is that like of things? So that is not getting difference very much. So here we plot this active sterile mixing angle with the right-hand neutrino mass, and this whole region is satisfied the baryon asymmetry. And now this we see that this region comes under the future predicted experiment of CEPC and FCCE. This is the circular collider of electron and positron. So
These are future bounds.
yeah, future bounds.
And present bounds is the gray area.
These bounds. I mean, these are various experiments, various Delphi,
So in
NS62.
other words, you can get the corrected baryon symmetry or a mixing between the active, the
And-
sterile mixing and neutrinos of the order of 10 to minus 8.
Okay.
But nowadays, the present bounds are 10
Very
to
much
minus
up.
4.
Yeah.
But in the future, you can.
So this experiment, I mean, promised that they can probe this range of neutrino mixing angle. So they run their experiments and see any signals they got or not.
I think the capturing that neutrino's double beta decay can up to reach 10 to the minus 6.
Okay.
Something from neutrino's double beta is.
Okay. And
Neutrino's double beta decay.
Present bounds. In other words, you suggest.
Yeah, no, I think the future can go as much as 10 to the minus 6, minus 7. Neutrino's double beta.
and these are the existing. I mean, up to that, the experiments can be done. Up to that,
Yes,
is
are
not-
you considered global constant?
yeah, this is, I mean, taken from, I mean, data taken from the papers, various papers.
Because maybe the neutrino's double beta decay will fall in this exclusion region most likely.
Okay.
Most likely.
Okay, I didn't
Maybe
check
some
that.
fluctuation will be there, but mostly.
And also below there is also a bound, this is called Sisovsky region, because we take lightest active neutrino mass is 0. So from this I mean the active state neutrino mixing, which is m nu, that is the active neutrino mass, divided by capital M, this is the right hand neutrino mass. So m nu is the total mass, we consider it. So if m1 is 0, then the other two right-handed the sum of other two active neutrino mass is fixed from the oscillation data. So that for we get a lower limit of this. So below this USSR cannot be there theoretically with this user region. So this is the range where we get the baryon symmetry, and that can be futurely probed by these two experiments from the measurements of this active state mixing angle. And so another detection.
In this plot, what are the parameters? So you have the mass.
This delta M we vary, and the imaginary part of theta.
So it's just a scatter plot. So you
Scatter
vary
plot.
them.
Yeah.
But you have fixed already lambda to the value, to the tuning value, so that it's 30.
Yeah.
So
So
everything else is fixed.
yeah, I mean here just we forget about the lambda part now. Okay, we just solve these Boltzmann equations with varying these parameters and get and just plot this up to 100 GeV mass from a lower right-handed neutrino mass. This low right-handed neutrino mass we fix from the nucleation. I mean, up to what nucleation temperature we can go, and the right-handed neutrino mass we have to be slightly greater than that nucleation temperature to be out of equilibrium decay to N, L, and H. So how I calculate the lower, the low mass, the lower right-handed neutrino mass we show in the next plot. So here just we discuss this first. So this upper panel, you see that there is a M1 minimum, that is the right-handed neutrino mass and the lowest right-handed neutrino mass. Now, suppose for a capital lambda, we have a fixed Tn. So to decay that right-handed neutrino, in that scenario, that right-handed neutrino mass should be greater than that Tn. So this way, we just calculate for every lambda the Tn, and for that, what is the right-hand neutrino mass, so that can decay and produce the baryon symmetry. We just fix the minimum mass of the right-hand neutrino for every case. I mean, suppose as a fact that this for here, so here this limit is different from that we show in the slides, because those are the calculated from taking the high temperature approximation that I said that we take for time being only. So this value is we get from taking care of full potential with the Coleman-Weinberg, full one loop calculation, that finite temperature calculation, daisy corrections, and the counter term as well. So we get the Tn minimum 33 GB with lambda is 572 GB, and the upper limit of 810 GB with the Tn maximum is 119 GB.
Lambda max was 750 GB.
That was taken for, when we take the consideration of high temperature potential, this approximated form. We just show that how we limit the values, but finally we calculate from the full potential and project it.
Okay, the 750 was like trimodal.
Yeah, trimodal for you, like kind of.
If you take full potential, it is like
810.
What was the lambda mean value of 586?
586 around. That was 72. Here we, very much effect we just neglect. The daisy correction we neglect. The one loop, the higher order correction we neglect. So if we add those terms also, the parameter somewhat changes. So upper part is this. So with this value, with the corresponding lambda, corresponding Tn, and the corresponding minimum right-hand Newton mass to get a bioinosymmetry, we just calculate it. And the lower panel. So there's a quantity delta lambda 3, which is related to the triple Higgs coupling. So inclusion of this dimension 6, the triple Higgs coupling is modified through this V0 Q by lambda square. V0 is the Higgs wave. So this is the lambda 3, and this is a standard model value, and this is the extra contribution due to inclusion of this dimension 6 term. Now if we plot, this with delta lambda 3 is delta lambda 3 minus lambda 3 SN by lambda 3 SN. So this blue line is for different lambda, we get a different lambda 3, and this different delta lambda 3. So we plot like this, and this 1 sigma, 2 sigma, 3 sigma is drawn based on that. HLLHC promised that they can measure this triple Higgs coupling with the 30% of precision. With the 30% of precision of that lambda 3 SN in the standard model value. So taking into account that this is supposed to be 1 sigma, this 2 sigma and 3 sigma region, and we show that our limit, that is between 572 and 810, we have a 2 point at 2 sigma, 3 sigma that can be detected in future at 2 sigma, 3 sigma level at HLLHC, if they can able.
So this triple coupling is what is the effect? It's changing the, how do you measure it?
This measure, I think, I just forgot the channel. Di-Higgs production, yeah. Di-Higgs production or Di-Higgs. Yeah. I did not remember about much about it, but I think Di-Higgs production on the channel. Yeah.
This is again in the future.
Yeah.
In other words, what you're saying is that you can have a right-hand neutrino of 30 GeV that is invisible.
Yeah.
And,
in terms of the active neutron mixing, it's still
because of
coupling small. So, and on top of that, as we have a fast order phase times in our scenario, we can also get gravitational waves from this. So here we take in contribution of only the sound waves from and the MHD turbulence, because so from fast order phase tension, three type of sources there for gravitational wave production. One is the bubble collision, and second is due to the expansion of the bubbles, there's a generation of sound waves in the plasma, and also after the generation of sound waves, there's the turbulence due to the magnetic field in the plasma that can be also a source. So from these three, we take here two for sound waves and the MHD turbulence, because for electric phase transitions, the bubble wall velocity for faster electric phase transition, the bubble wall velocity is less than the sound wave. It can be greater than the sound wave, but it's a very fine-tuned or very stringent situation, but in general, normally the bubble wave velocity is less than the sound wave. There is a subsonic region. So for that case, the gravitational wave contribution from bubble collision is suppressed, is not dominated. So for subsonic bubble wave velocity, the sound waves and the imagery turbulence may give the dominance to generate the gravitational waves. So we just take these two configurations or two generation wave, and for each lambda we get a signal with a different strength, because for each lambda we get a Tn. Actually this amplitude or frequency depends on the alpha star, beta, VW and Tn. So we just forgot to read. Okay, so alpha star is the latent heat. At that time the phase transition happenings, the latent heat released due to the transitions. That means the difference in energy between the false and the true vacuum. And beta is the duration of phase transition. It starts from Tn and then it ends at some temperature. So from Tn to that temperature, that duration is measured by the quantity beta. BW is the bubble wall velocity, and Tn is the nucleation temperature. So
alpha and beta depend on the potential.
On the potential, Tn also depend on the potential lambda. So depend on lambda. So alpha, beta, and Tn all depend on a particular lambda. So for a particular lambda, we get alpha, beta, and Tn, and we assume the VW is less than Cs. So any value, suppose 0.5. Cs is 0.55. Suppose 0.5. If VW is fixed. Yeah, the sound speed. So with different lambda, with different Tn, alpha, and beta, we get a different frequency, peak frequency, and the signal.
So now the frequency is quite low. So compared, because usually phase transitions are very high.
High temperature. If we go high temperature,
this is extremely low.
Extremely low temperature.
So the principle is measurable.
Yeah. So in LISA, and these are also the future sensitivities: LISA, Resigo, and BBO.
And how much time do you need?
Yeah. Okay.
Can you summarize?
Yeah. This is the last slide.
Last slide.
Yeah. So, just thank you.